Hi, welcome you all to my channel. Today we'll discuss how to design a digital filters. Actually, so far we don't have any direct methods to design the digital filters. First, we have to design an analog filter whose transfer functions has to be defined something like HA of S, which is equal to the Laplace transform of an output divided by the Laplace transform of an input. I mean, for stable and causal realization of the analog filters, the transfer function HA of S must be a rational function in terms of S, and another important criteria that has to be satisfied is the all coefficients of S must be a real number. And another one is to define the stability of an analog filter. For example, as all of you know, let us consider this is an S plane as S equal to sigma plus j omega, and we will be considering the real part of the sigma on x-axis and omega will be on y-axis. To satisfy the condition of stability of a filter, all poles must lie on the left half of the S-plane. This is the mandatory condition to realize an analog filter which is to be stable and a causal. And second thing is to transform this analog filter into a digital filter. Let us write this h of omega is a digital filter transfer function. So far I told you we don't have any direct method to realize the digital filters. Only the thing is we have to design an analog function that has to be transformed into a digital filter by following any one of the technique. As all of you know, we have a basically some fundamental methods are there. One is a derivative of approximation method, and the second one is impulse invariant transformation method, and the third one is bilinear transformation. As the first two methods, derivative of approximation and impulse invariant transformation method, these two are suitable for the realization of low pass filters and band pass filters at low resonant frequencies. The limitation of these two filters, derivative of approximation and impulse invariant transformation methods, these two are suitable for designing of low pass filters and band pass filters at low resonant frequencies. This problem has to be overcome with the help of a bilinear transformation, which is suitable for the designing of high pass filters and a band rejection filters at high resonant frequencies omega r. Let us see how do we transform a given analog transfer function into a digital transfer function. For example, let us assume HA of S is analog transfer function. It has to be transformed into H of omega, which is nothing but the desired transfer function of a digital filter. The simple method only we have to apply one simple transformation is, let h of omega is transfer function of a digital filter such that it has to be realized using a transfer function of an analog filter h of s, where in place of s simply substitute 2 by t tan of omega by 2, where this omega is resonant frequency of the desired digital filter and t is the time period. The time period t has to be realized or find simply using the formula t equal to 2 by omega tan omega by 2, where this omega is analog frequency and this omega is digital frequency. Omega is analog filter frequency and omega is digital filter frequency. See, simply by using this simple transformation h of s, which is equal to ha of s, and s has to be replaced with a simple transformation s equal to 2 by t tan omega by 2. So using this simple transformation,